Hello everybody. Here is your lesson 2 science lesson. We are going to be discussing, sorry, I had to find my water bottle. Can't do a video without it, right, Cash? So we're going to be discussing, we discussed before Newton's first law. We're going to be discussing Newton's second and third law and what work is. So let's go over Newton's first law first. Newton's first law is an object at rest will remain at rest, and an object in motion will remain in motion in a straight line at a constant speed as long as there are no other forces acting on it. It's a lot of words, but basically it's saying, if I were to summarize it, I would say a thing will stay doing whatever it's doing. If it's just sitting still, if it's traveling, it will keep doing what it's doing unless there's a force that acts on it. Okay? Does that make sense? And that's called inertia. Inertia means it will keep doing what it's doing unless there's a force that acts on it. It takes a force to make it stop doing whatever it's doing. That's Newton's first law. We're going to go over Newton's second and third laws today. Newton's second law is actually summed up by an equation. I can show you here. Okay? This is it simply. F equals m times a. You might say, wait a minute, there are no numbers in there, okay? And we actually can rearrange this to be, what it actually is A equals F divided by m. A equals F divided by m. Now what does that mean? That means acceleration equals force divided by mass. Acceleration equals force divided by mass. That's Newton's second law. And so what does that mean? If I were to explain it, it's saying that the acceleration of an object, you know how you give an object an acceleration. Let's say, picture this in your mind. You are making a soccer ball accelerate across the soccer field, right? How could you do that? Let's see, who's a soccer player here? Caleb. How would you accelerate a soccer ball across a soccer field? Pretty simply, you could kick it, right? Maybe you could head it, but probably kick it, most likely, right? So what did you do? You applied a force, okay? Well, here's the thing. How do we know what type of acceleration happens on that ball? Well, it all depends on the mass the ball has. So if you take a force, you apply a certain force to a ball. If you divide that by the mass that ball has, that will give you the acceleration. I dropped my phone. Okay? All right. Now let me talk to you about certain principles here. If I should have grabbed a couple different color markers. Okay? In an equation like this, let me show you. Let me show you something cool about math. Okay, is this a correct math sentence? 20 divided by 4 equals 5. I think you'd all agree with me that 20 divided by 4 equals 5, right? Am I right? Yeah. Okay. Now let's say I make the bottom number bigger. Let's say I make it 10, okay? And keep the top number the same, 20, okay, 20. Let me put them on the other side to make it a little easier. Okay, I did this. 20 divided by 4 equals 5. It's a little easier to look at, right? Well, let's say I keep this 20 the same, 20. This time I'm going to divide it by a bigger number. I'm going to take this number on the bottom and make it bigger. Let's see what happens to our answer. 20 divided by 10, okay? So instead of 20 divided by 4, I took this 4 and made it bigger, right? 20 divided by 10 equals what? 2. What happened to my answer? If I made the bottom bigger, the answer gets smaller, right? And that happens every time with every kind of division problem. Let's try another one. Let's say 8. No, let's not go with 8. Let's go with 12. 12 divided by 4 equals 3, right? 12 divided by 6, so I made this bigger, equals 2. The answer gets smaller, right? Doesn't that happen? So when you make the bottom bigger in that type of thing, where it's just a division problem, when you make the bottom bigger, the answer gets smaller. That means the bottom part on the division problem and the answer it's a big word, indirectly proportional. What that means is that the opposite thing happens. When you make the bottom bigger, the answer gets smaller. If you make the bottom smaller, the answer is going to get bigger. So let's look at that equation again. Force divided by mass equals acceleration. And let's see if you agree about this. Force divided by mass equals acceleration. So according to that, remember the top was the 20, the bottom was the 4, and the acceleration was the answer, right? If I make the bottom bigger, what happened to the answer? The answer got smaller. So let's say I have the same amount of force I'm applying to a soccer ball. Okay, apply a certain force to a ball, okay, to a soccer ball. And that soccer ball has a certain mass, it's going to have a certain acceleration. But what if I apply that same amount of force to an object of a bigger mass? Let's say a bowling ball. Okay, apply the same force to a bowling ball, what's going to happen? Yes, my foot's going to hurt. Other than my foot hurting, what's going to happen to the ball? Is it going to have the same acceleration? Is it going to fly off at the same rate? No, of course not. That bowling ball is not going to go as fast as the soccer ball is. Maybe go a little bit, but it's not going to really fly that much because it has a much bigger mass. So much smaller acceleration. See, the bottom and the answer are opposites. Okay, let's look at that equation again and see what happens when the top changes. Okay, let's go with 20 divided by 4 again. Okay, 20 divided by 4 equals 5. Right? Right. Let's keep the bottom, the 4. Let's gonna keep the 4 the same, but we're gonna make the top bigger. Okay. The top becomes, let's double it, make it 40 divided by 4. What happens to the answer? Oh, this time when the top gets bigger, the answer gets bigger too. The top gets bigger, the answer gets bigger. So the top thing, the same thing happens. They're not opposites. They're directly proportional. Whatever happens to one happens to the other. If the top gets bigger, the answer gets bigger. Does that make sense? So, and I know this seems like math to a lot of you, but the thing is, this is physics, and physics has a lot of math in it. It's math and science together. So if you like math and science, physics is for you. Okay, so as I said, the top, just like remember I said the bottom is the opposite. So when the mass gets bigger, the answer, acceleration, gets smaller. Well, here we have force divided by mass equals acceleration. Okay, and so with this equation, now we would talk about the top. When the top gets bigger, that means the answer is going to get bigger. What does it mean to make the top bigger? Well, that means you're going to be adding more force, right? If I take the soccer ball, and we're keeping the mass the same this time, so we're not switching the ball, we're just going to stick with the soccer ball. I kick the soccer ball with a certain mass, I'm going to get a certain acceleration. What happens if I kick the ball with twice as much force? It has the same mass, right? Twice as much force. You're going to expect it to what? Go off with twice as big of an acceleration. That's what Newton's law says. Newton's law says whatever force you have divided by whatever mass you have is going to give you an acceleration, or your acceleration is given by whatever force you apply to the object divided by that object's mass. Does that make sense to you guys? So the more force, the more acceleration. The more mass, the less acceleration. That is Newton's second law. Okay? Quick drink. Okay. Recap. Newton's first law. An object at rest will remain at rest, an object in motion will remain in motion, a straight line on constant speed, as long as there are no other forces acting on it. So basically, something will keep doing what it's doing unless you apply a force to it. Newton's second law, the acceleration of an object is going to be given by whatever force you apply to that object divided by the mass. Okay, and we're actually going to do some problems. I'm going to give you some problems like that on the test. They won't be difficult. It'll be something like, remember, let me write it again before I move on. Force divided by mass equals acceleration. This will be the type of thing that I'll put on your test. Okay, watch. Okay, force divided by mass equals acceleration. It'll be like a word problem. I'll say, You apply a force of 10 newtons, because that's a unit for force, it's newtons. You apply a force of 10 newtons to an object that has a mass of 2 kilograms. What is the acceleration? Let me say it again. You apply a force of 10 to an object with a mass of 2. What is the acceleration? Well, force divided by mass. What was your force? 10. What was your mass? 2. Can you do that math? 10 divided by 2 equals 5. Let's do another one. You apply a mass of, you should all be able to do it in your head. You apply you apply a force of 15 newtons to something with a mass of 5 kilograms. So a force of 15 newtons applied to a mass of 5 kilograms. What would your acceleration be? 15 divided by 5 equals 3. Very good. Okay, let's try one more. You apply a force of 30 newtons to something with a mass of 6 kilograms. What would your acceleration be? 30 newtons divided by 6 kilograms equals 5, right? The units for acceleration, meters per second squared. Okay, does that make sense to everybody? That's Newton's second law. I'm going to give you a couple problems like that on the test, and they're going to be that easy. So hopefully you guys shouldn't have any problem with that math. All right, so I'm not even kind of going by the book here. So that's Newton's second law. I'm basically summarizing page F18 and F19, what affects acceleration and how is acceleration calculated on page F20. So what I just said is basically F18, F19, and F20 summarized, okay? Whoa. F21 discusses Newton's third law, balanced and unbalanced forces, okay? What a balanced force is something where if you picture, a balanced force is something, picture a tug of war with a rope. Let's say that Kayleen is in a tug of war with all the boys, okay? And obviously what would happen is Kayleen would be holding the rope and all of the boys on the other side would be going, rah! And Kayleen would just hold it with one hand like, yeah, let's go, that's fine, yep, doop, right? But anyway, let's say they're at a standstill and the rope is going, it's gripping and nobody's moving it, okay? You know how that happens sometimes with tug of war, nobody's moving? That would be a balanced force because there's the same amount of force on each side. They're balanced. An unbalanced force would be if Kayleen's like, all right, I'm done fooling around, just goes, and pulls all the boys forward into that big mud puddle. That would be an unbalanced force. What happened was, if I draw it out, this is the balanced force. Okay, here's Kayleen on this side. And here's all the boys on the other side. So here's balanced, okay? There's a force of this much this way and a force of this much this way, okay? That's balanced. As soon as Kayleen says, all right, I'm done playing around, what happens is this force arrow for Kayleen becomes this long, okay? Look at it. So this force arrow is longer than this one. This is Kayleen, this is all the boys. Look at it. There's this much versus this much. Well, if I were to take this arrow, okay, which is this long, I were to show it compared to here, look how much longer her arrow is, okay? It's about this much longer. This would be the remaining force. So she has that much more force than them. We could even put numbers with this. We could put this as 30 and this as 50. Okay, 30 is bigger than 50. Did I make those up? Yeah. 30 is bigger than 50, right? So that's an unbalanced force. Well, what happens when there are balanced and unbalanced forces? Balanced forces, there is no acceleration. Unbalanced forces, there is an acceleration. Whenever you see an acceleration, okay, you can put it either way. Whenever you see something accelerate, that means that there was some sort of unbalanced force, okay? Whenever you see something not accelerating, that means that all the forces are balanced. Reverse it. If you have a balanced force, it will not accelerate. If you have unbalanced forces in any way, it will accelerate. Okay? Does that make sense? That's still part of Newton's second law. So, oh, this is a cool thing. On F-23, there's a picture of a balloon, okay? This is picture on F-23, right here. This picture is what I'm talking about. Look at that picture. So, in the first part, you see all the arrows are going outward. You have the red arrows and the blue arrows. What are each of those? Well, the blue arrows are the force of the helium or the air on the inside of the balloon. The helium or the air on the inside of the balloon is pushing outward. It wants to get out. It has a lot of force, outward force. The red arrows are the force of the balloon, that the elasticity, the structure of the balloon pulling inward, okay? And they are currently in that state. They are balanced, okay? You can see all of the arrows are the same length, okay? Usually when we draw arrows, force arrows or vector arrows, they're going to be the same length if they're the same amount. If one's bigger, you're going to draw that arrow bigger. But all those arrows are the same length, so what that means is all the forces are balanced in that balloon. So that balloon is just going to stay the way it is, right? The air is going to stay in it. Look at the second balloon. Well, what happens is you make a hole in it, and you notice, look at where it says A and B. You guys see at the top of the balloon where it says A and B on page F-23, it says A and B. Well, A is pushing up and B is pushing down. There's all the different red and blue arrows on the sides. Those don't do anything because the balloon can't come in at all and the air can't go out at all that direction. So they stay where they are. But A and B, A is pushing up and B is pushing down. All of a sudden when you open the bottom, B has an exit. B has been pushing down but has nowhere to go. Now once you open it up, B has a place to go. B shoots down through the bottom, and now what happens is that B arrow, the red, B arrow there, it grows smaller because it's depressing, and then the A arrow with the air pushes outward, pushes upward. Okay, so that's what happens when you undo a balloon. It goes like goes all around. Is that forces are becoming unbalanced, and so there is some sort of acceleration. That's called thrust as well. It's kind of how a rocket works. All right, let's delve deeper into Newton's third law here. Newton's third law is an action and reaction idea. Newton's third law says, for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. Okay? What does that mean? That means that whatever happens, there's something that reacts because of it. For instance, if I go like this and I punch a brick wall, okay, me punching, my force on the brick wall is an action. There's going to be a reaction. I'm applying a force to the brick wall. But the thing is, that's the action, but there's always a reaction back. The brick wall also applies a force on my hand. That's why you can't just punch a brick wall and be like, yeah, that's fine, my hand's fine. No, because whatever force I apply to the brick wall is applying also on me, okay? So for every action, there's an equal and opposite reaction. If I apply a small force to the brick wall is also applying a small force to my hand. If I apply a large force to the brick wall is applying a large force on me. For every action, there's an equal and opposite reaction. Okay, it's action, reaction. Does that make sense to everybody? That's Newton's third law. Okay. Let's see, is there anything else I'm going to cover about this? There's more to this lesson. I'm probably going to do another video tomorrow on work and simple machines. I'm basically at 20 minutes right now, though, so I don't want to go too deep. So that was Newton's second and third law. I'm going to go into work and machines tomorrow. I will recap, though. Let me recap one more time what Newton's three laws of motion are. Number one, an object at rest will remain at rest, and an object in motion will remain in motion, straight line, and constant speed as long as there are no forces acting on it. Basically, it will keep doing what it's doing as long as you have no forces acting on it. Now, that applies to, let's say you kick a soccer ball. You say, Mr. Hanley, I kicked a soccer ball across the field and eventually it slows down. Nobody else applied a force by kicking it. No, but the grass applies a certain force. What a force? Let me ask you. Kayleen, what force does the grass apply to the ball as the ball's traveling across the field? Do you remember what that force is called? It's called friction. It's called friction. Friction that grass is applying to the ball. That's why it slows down. If the grass wasn't there and there was no friction, that ball would literally keep going forever. Okay, that's Newton's first law. It will keep doing what it's doing unless a force acts on it. Newton's second law. Acceleration equals force divided by mass. The acceleration is equal to the amount of force that you apply to an object divided by the amount of mass the object has. That will give you whatever the acceleration will be. And Newton's third law, for every action, there's an equal and opposite reaction. Meaning, when I apply a force to something, it is also applying a force back on me. Right? They come in pairs. The forces come in pairs. All right, those are Newton's three laws. We're going to pick up back at page F26 tomorrow.